Let's do some more practice writing Lewis structures. And this is part 2, so we'll try some that present some exceptions to the rule. And let's take as our first example BF3, boron trifluoride. When I look at the periodic table, here's boron. Boron is an S2P1, so it only has 3 valence. And fluoride is a halogen with 7. So I only have 3 with boron and 7 for each fluorine. 3 7s are 21, and 3 gives me 24 electrons for this whole molecule. And boron is central. It's the least electronegative. In fact, fluorine is the most electronegative element in the periodic table. I'm just going to arrange, I haven't left much room there, my fluorines around the boron. Now I'm going to make single bonds written as a pair of electrons, illustrated as a dash, 2, 4, 6. And again, I want to go on the outside to use up the rest of my electrons with the aim of making an octet of electrons around each of the fluorines. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, I need to get to 24, 20, 22, 24. So boron is electron deficient. I only have 2, 4, 6, whereas each of the fluorine has 8. So I could take this pair and put it here or anyone, and I would have a double bond, in which case that would make 8 around boron. But boron presents an exception. And if you see where it is, boron only has 3 valence. That's part of its exception to the rule. So in the same way that hydrogen only handles 2 electrons around it as an atom, and not 8, boron does not take 8 electrons either. In fact, it actually takes 6. So this is an exception to the rule, to the Lewis structure principle of an octet of electrons, and it falls under the description of electron deficient because it has 2, 4, 6. So it sounds like it's a problem, but it's not. In fact, if I do the formal charges on this one, boron has a number of valence. It has 3, and it'll be 3 minus half of the bonding electrons minus all of the non-bonding electrons, and so it has a formal charge of 0, which is as favorable as can be. The fluorines, presumably each of them, because they're all the same, has the same formal charge of 0 because it has to add up to 0, but let's just verify. 7 valence electrons minus half of the bonding, so that would be 1, minus all of the non-bonding, 1, 2, 3, 4, 5, 6. So each fluorine has a formal charge of 0. So the total is the formal charge on BF3, boron trifluoride, is 0. And that's great. That's the way it should be. So that's our first exception. All right. And if I just pull the periodic table back here for a moment, you might see a compound with beryllium, for example, beryllium chloride. I said we wouldn't use this localized electron bonding in our considerations for any molecules of significant ionic character, but beryllium is a central atom in these examples, and it's an example of an electron deficient atom. So as a central atom, it does not take 8, it takes 4, but 4 electrons. But the one that we'll see the most often as electron deficient, i.e. not handling 8 electrons around it, is boron, and boron takes 6. And once we get to carbon, we're back to 8 and forward. Okay? So that's our first exception. All right, let's do another one. How about CO3 2-? This is the carbonate ion. The carbonate ion has a charge of 2 minus. And I said good practice for your lowest structures was to go back in Chapter 3 to your polyatomic ion list and practice. So here we go. 6 valence electrons each from oxygen. 3 6s are 18. Plus 4 is 22. Plus 2 more is 24. So I have 24 electrons total valence in my CO3 molecule. Place the least electronegative atom in the center and arrange the atoms around it. Make single bonds. 2, 4, 6. Go to the outside, complete the octet. 8, 10, 12, 14, 16, 18, 20, 22, and 24. So I have a problem with carbon. You're probably never going to put a lone pair on carbon anyways, so typically you either make it works out, or you're short, in which case if you're short like we are here, we have to take a pair and share it as a double bond instead of a single. That way I'm counting it for O, and I also get to count it for C, and that'll bring this up to 2, 4, 6, 8. Now I have a choice. I could put it here, I could put the double bond here, or here. And so I'm just going to indicate that that's my plan of action. And I have 3 possible Lewis structures. And I'm going to draw them. I have a double bond, a single, and a single. So 2, 4, 6, 8. And that's a 2 minus ion. And I draw the arrow like this to indicate that I have more than one possible structure. And in fact, this is called resonance. The name is rather unfortunate because it might imply, like a bell, that it's kind of resonating between these two. It's not really. It's not at any instant in time the double bond here, or as I'm going to draw here, the double bond in the middle. It's really all the time a blend of the 3 structures, 3 possible structures that I'm going to draw. There we go. 2 minus, and my third resonance structure. So there are 3 possible resonance structures for the carbonate ion. Two minus. The double bond can be here, or here, or here. And it's called resonance. Now I can pick any of these because the environment around each of the oxygens and carbon is the same in each of these. So I just want to do the formal charge. Let's just pick this one for practice. Formal charge on carbon. It is 4 valence minus 1, 2, 3, 4 minus, of course, I never have any lone pairs on carbon. So that carbon's very happy with a formal charge of 0. Hydrogen, or sorry, there's no hydrogens in here. How about the double bonded oxygen? I'm going to differentiate that from the single bond. So the double bonded oxygen is 6 minus 2 minus 4, right? Half of the bonding, 6 minus 2 minus 4. So that's 0. So it's very stable, a double bonded oxygen like that. Each of the single bonded oxygens, they'll have a different formal charge. I start off with 6 valence minus, let's look up here, half of the bonding, which is 1, and 1, 2, 3, 4, 5, 6, all of the non-bonding, and that gives me minus 1. So when I want to actually label the formal charges on this diagram and not have it look like an oxidation number or a real charge, I put a circle around it. So each of the oxygens single bond, that's minus 1, minus 1. Carbon was 0, and this oxygen was 0. And that's how if I want to label it, and you'll be asked to probably on the exam, I do it like this, and I can clearly see that the sum is equal to the real charge. And I can do that on each of my resonance structures. When you do a few of these, you will recognize that a single bonded oxygen like this is always going to be a -1, and this double bond is a 0. Don't assume that, though. You still want to work it out. And I've got -1, -1, and 0. So that's a really complete answer. Let's stop this one here, and we'll do some more. Oops, hope that wasn't like that. We'll do some more examples in a moment.